Hey everyone, welcome back to AP Stats. Today's Stats Medic has us transforming probability distributions. And so to get us started, it's time for a raise. So Mr. Ferraria's employees have been working very hard and he thinks it's time to give them a raise. He's trying to decide if he should give everyone a $10 raise, just add $10 per hour, or double everyone's wage multiplied by 2. So the first thing we're going to do is look at the data that we got from yesterday. And as you can see, a probability of having a wage of $1 a day was 12 out of 39. $25 a day, that was 1 out of 39. Last time we calculated the mean at $3.769, so about 377, with a standard deviation of 4.56. Look at yesterday if you don't remember how we did that. Now, to make a decision about what raise should be given, we're going to complete the two tables below and we're going to calculate the new mean and the new standard deviation. So, what happens if we if we add $10 to everybody's wage? So this new wage over here was $1. We're going to add $10, so that's going to be $11. Then right on down the line, $15, $17, $20, $25, etc. The probabilities aren't going to change. There's still the same probability of getting any of those wages, only now the probability of getting $11 is 12 out of 39. So here's our new probability, and now we got to calculate the mean and the standard deviation. This time I thought we'd actually go to the calculator, so let's take a look at the calculator. Push Stat and then Edit number 1 to get to the lists, and then we're going to put all the wages in list 1, and then all of those probabilities in list 2. At this point, I realized that I put all the probabilities incorrectly, and these should be 12 out of 29, 8 out of 29. So I've already made those adjustments. The actual mean is 5.069, and the actual standard deviation is 7.209. So coming back to our calculator, and if we go to our lists, I do have all of the correct probabilities in there now. Just kind of take a quick check. 40, 41, that's 41, 61, 68, 78, 80. Yeah, this looks like it should add up to 1. All right, so now that we've done that, we're going to go ahead and calculate the mean and the new mean and the standard deviation, which you probably saw me doing over here. But I'm going to clear that off and tell you what I'm doing. The first thing we're going to have to figure out is the mean. So I'm going to go ahead and go second Stat, Math, and we need to add things together. So we're going to go sum. So we're going to multiply the wages, which were in L1, multiplied by the probabilities, which were in L2, and then we're just going to add those together. So this command right here will give me the mean. Okay, so there's my mean, 15.069. What I'm going to do is I'm going to store that as the letter M so that I don't have to keep typing in that number. Now the next thing to do is to find that standard deviation. So the standard deviation is the square root of, so we'll put a square root. And then it's a sum, so if we remember where the sum was, second Stat, Math, 5 for sum. So we're going to add together the deviations, which were L1 minus the mean, which if you remember that was an M, minus the mean, square it. Now we have squared deviations, and then we multiply by the probabilities, which were in L2. So this should give me the standard deviation, 5.12. coming back to the paper, now I did realize that I made a mistake on the standard deviation before, but now it's corrected. The old mean was 5.069 and the old standard deviation was 5.125. And if we add 10, the new mean is 15.069 and the standard deviation is still 5.125. Now we did these all the long way, so there really shouldn't, if there was some kind of a chance thing, it probably would have shown up. So this is actually what happens. How did adding a constant affect the mean and the standard deviation? Well, the new mean is the old mean plus a constant, and this new standard deviation is the same as the old standard deviation. So the standard deviation doesn't change if you just add the same number to every outcome. Let's check out the second one. Now we're going to double the wages. So we're going to take the wages and we're going to multiply by 2. And then the probabilities are going to be exactly the same. So there we go. The new wages multiplied by 2, the same standard deviations. Let's go over to our calculator and go to the same one. Now we're going to take this list over here and, well, we're going to turn this into the new wages. Okay, new wages over here. Let's go to the home screen and we're going to do the exact same thing. We're going to find our mean. So our new mean is 10.138. And then now we're going to find our standard deviation. So there we go with our new standard deviation. It's 20.591. So here we go with our numbers back in place. And do we notice anything interesting here? Well, the first thing I notice is the mean is 10.138. And if we look at the old mean, that was 5.069. Any ideas what 5.069 multiplied by 2 is? If you're guessing 10.138, you're right. Now what about the standard deviation? 5.125 multiplied by 2, that is 10.25. So what did multiplying by a constant do? So the new mean is the old mean multiplied by that constant, and the new standard deviation is the old standard deviation multiplied by the constant. Now, which option would you prefer? Now, that's an interesting one because there's a couple of ways that you can think about this. And the first one is, well, the maximum wage that you could probably get is higher if you go for the doubling, because you get 50. But at the same time, your minimum is still 2. So if we look at the mean and the standard deviation, it looks like a typical wage would be somewhere between $0 and $20. Whereas over here, if we add $10, a typical wage would be somewhere between $10 and $20. So it means a lot for the lower end of the spectrum, which is where most people are going to fall from this distribution. So it looks like, or if I was going to say, then I would say that I'd prefer the first one. So in option 1, you're kind of guaranteed a minimum wage of at least $10. And most likely, you are going to get a maximum wage somewhere near what you would typically get from option 2 as well. So I'm guessing option 1's probably better. Now, what about our important ideas? So if we add a constant c to every value, the shape is going to stay the same, which is why the variability stays the same, incidentally. And the center is going to be c. You're going to add that same value c to the old center. So if you add $10 to everyone's wage, the new mean is going to be the old mean plus 10 as well. Now, if you multiply by a constant, the shape is going to stay the same. It's just going to be stretched out or kind of compressed in. But, they'll be, in the geometric sense, a similar shape. The center will be multiplied by that same value c, and the variability will also be multiplied by that same value c. We have some equations here. The old standard deviation gets transformed to C times the old standard deviation. And if the old variance was sigma squared, the new variance is sigma squared multiplied by C squared. Let's see this first one. A large auto dealership keeps track of sales made during each hour of the day. Let X be the number of cars sold in the first hour of business on a randomly selected Friday. Based on records, this is a probability distribution. So random variable X has a mean of 1.1 and a standard deviation of 0.943. Well, we don't have to compute that. That's nice. Suppose the dealership's manager receives a $500 bonus for the company for each car sold. Let Y be the bonus received from the car sales during the first hour on a randomly selected Friday. Sketch the probability distribution X and a separate graph of the probability distribution Y. How do the shapes compare? So first off, the sketching the probability distribution here would mean creating that histogram. So here's that histogram. Notice 0 car sold goes up to 30%, 1 car sold goes up to 40%, etc., etc. Also, each one of these histogram bars are centered at the integer values. That is the standard practice for this kind of discrete probability distribution. Now let's do Y, which is the bonus received. Now I know it might be kind of hard to see, but the bonus distribution is the same shape as this distribution for the car sold. It's just kind of expanded a bit. So similar in the geometric sense, I think that's how we should say. Okay, they are similar. Next, let's find the mean of Y. So we'll grab our calculator again, and we'll go to Stat, Edit, and then we'll put in the values for Y. And I realized that I made a mistake on the distribution here of the bonuses, and that's really what I did. I think I put a 3,000 instead of a 1,500. So yeah, now looking at them, they look very similar, just expanded, like I said. This bar goes from negative 0.5 to positive 0.5. This one goes from negative 250 to positive 250. So that's what we mean by expanded. But literally the same looking shape now. Here's our data in the calculator. And then I'm going to show you another shortcut here on the calculator. So I hope this is going to be okay with you. But if I'm going to calculate the mean and the standard deviation, if we go to the home screen and we do Stat, Calculate, one variable statistics, this time we change the frequency list to L2, push Calculate. Now this is going to give me the mean and the standard deviation here. So this is the mean and standard deviation, the super shortcut way on the calculator. So that mean is $550 and the standard deviation is 471. Interpreting Y is if we computed the bonuses from many Fridays, the average bonus would typically vary from the mean of $550 by about $471.69. Now lastly here, the manager spends $75 to provide coffee and donuts to prospective customers each morning. So the manager's net profit T during the first hour on a randomly selected Friday is $75 less than the bonus earned. Describe the shape, center, and variability of the probability distribution for T. First off, the shape of T is going to be exactly the same as the shape of Y. Next, the center of T is going to be $50 less than the center of Y. So the mean of t is the mean of y minus 75, sorry. And lastly, the variability, since we're only adding a negative 75 to every value, we're not multiplying, the variability is going to stay the same. So the standard deviation of t is equal to the same as the standard deviation of y, which is 471.69. So that's it for our 6.2 day 1, and we'll see you next time here on Stats. Peace.